Okay, are we good?
Did it say it's recording there? Let's make this go on.
Yes. Okay, everyone. Hi, welcome to session 6C in STOC 2020. We have an exciting upcoming session on optimization in LP solvers with many great and breakthrough results. As you probably know the drill by now. Each speaker gets a 5-minute presentation session followed by a 5-minute Q&A. You can feel free to raise your hand or to post questions in the Q&A box. We, the host, will monitor those, and we will defer the questions till the end of the talk. If we don't have time to answer all of them, we will just defer them to either discussion in the Slack channel, or you can remain after the session. We will try to hang out for another 20-30 minutes. So hopefully the speakers can take remaining questions there. I think that's about it. So our first speaker is Bento Natura. He's going to talk about a scaling invariant algorithm for linear programming whose running time depends only on the constraint matrix. Bento, feel free to share your screen. And
yeah, thank you very much. This is joint work with Daniel Dadouche and Sophie Halberts from CWI Amsterdam and Lazi Weg from LSE. So the problem we are concerned about doesn't need any introduction. It's linear programming. We aim to minimize the linear objective over linear equality constraints and want that x is not negative. And since the late 70s and early 80s, we have weakly polynomial solvers in the ellipsoid method and interior point methods. So those are algorithms that are polynomial in the dimension of the problem n and m and the bit complexity L of the problem. And the big open question since then is the quest for a strongly polynomial algorithm. So essentially the holy grail of the area that asks to drop the dependency on L. So only dependence on polynomial in n and m, which is also famously known as Smale-Snelf question. What we are concerned about in this paper is dependence on the constraint matrix only. So we allow dependence on A, but not on the right-hand side B or the objective C of the problem. This has been done in breakthrough work by Eva Tadeusz in the mid-80s already. She needs that A is integral, and if then the subdeterminants are bounded by some value delta, then her algorithm solves LP that is polynomial in M and log delta. And this has been a decade later generalized by Vavassis and Ye in the mid-90s. For them, A can be any real valued matrix, and they use LASD squared interior point method that runs in polynomial time M, N, and log chi bar, where chi bar is some condition number of the constraint matrix. And this is also bounded in delta. That is why it's really a generalization of Tadeusz's result. In general, they use an interior point method, and interior point methods are usually scaling invariant under column rescalings, but the Vavassis algorithm is not scaling invariant. So at a crucial point of their algorithm, they group together or layer together variables based on their value, which is inherently not scaling invariant. Furthermore, this condition number chi bar that they use is also not scaling invariant. So an open question was whether there exists a LASD squared method, some modification of their algorithm that would be scaling invariant, which would automatically give an algorithm that is not in runtime dependent on log chi bar of the original matrix A, but this chi bar of the optimal rescaling, say I prime, of the matrix A. And this is our contribution. Our main result is that we find such a modification, a scaling invariant algorithm for interior point method, and thereby also settling an open question that was posed by Renato Montero and Takashi Tsuchiya in 2003. And now if we define as chi bar star this optimal rescaling of the constraint matrix A, which can be arbitrarily much smaller than chi bar, so not even polynomially bounded in the dimension m or n, then our algorithm is solves LP in n to the 2.5 log chi bar star, essentially linear system solves, which we achieve by also an improved analysis that could also be applied to the Vavassis algorithm itself, which crucially needs log chi bar. which crucially has log chi-bar dependence and also a factor essentially of n more in the runtime. In the remaining 1 or 2 minutes, I want to introduce a quantity that was central to our formulation of the algorithm, to our analysis, and was already important in the follow-up paper to this, and that we think is going to be central to find strongly polynomial algorithms for either special classes of LP or even linear programs themselves, and that is the circuit imbalance measure, which can be seen as kind of a combinatorial version of chi-bar. So how is it defined? We define circuits of our constraint matrix A as minimal linearly dependent subsets of the columns. And then you can define for every pair of variables the circuit imbalance kappa ij, which is essentially the ratio between the two for a vector x in the kernel that represents this kernel element, which represents this circuit. And then you can define the circuit imbalance measure of the full matrix as the maximum over these quantities kappa ij. Now this is a nice combinatorial measure. It is approximated, or it approximates chi-bar itself. And I want to close with a nice min-max characterization of an optimal rescaling kappa star. So I didn't formally define it, but it's equivalently defined to chi-bar star. And that is what you can see on the lower left corner. The optimal rescaling of such a column, an optimal column rescaling can be found by solving a max-mean cycle problem, or say a multiplicative max-mean cycle problem, where the edge weights are these circuit imbalance kappa ij. I think this is a nice point to stop. And I think we really need to, in future, study this kappa, because we feel that there's much more to get out of it, as I mentioned before introducing it. Thank you.
Okay, thank you very much. I see one question, so I'll allow the speaker, can you hear us?
Yeah, I see the question.
Okay, so maybe, I don't know if I should, I guess I'll read it. So the question is,
okay.
Do any experts believe that one can entirely eliminate the dependence of the LP arithmetic complexity from any kind of condition number? I'm inclined to believe that this dependence obstructs strongly polynomial time algorithms.
Okay, so what we certainly know is that this approach will not lead to a strongly polynomial algorithm, as it was shown a couple of years back that interior point methods, if you lose the standard log barrier, are not going to be strongly polynomial. In general, LP and condition numbers, this is of course an open question, and I know of Dan and Latzi, who both are not sure, so they both they're essentially unsure if it is possible or not.
Okay, great. I see, and I think we have a time for at least for, let's say, one or two more questions.
Yeah, I see.
Okay, so Bento, you should read the question and answer it as well.
Okay, another question is, weekly IPM takes root n iterations and your improved result for strongly takes n to the 2.5. Can you briefly talk about the reason for this gap and whether one might be able to get a better iteration bound? Yeah, the idea is essentially that if you look for weakly polynomial solvers who get the root n, then in this model you only need to go down the central path to something that is 2 to the minus L, and then you're able to round to an optimal solution, which is not possible if you look at the real number model, and therefore you need to make progress in a different kind, and that is why we need this layers least squared method that makes faster progress for straight parts. So this is better explained in the long part, and it would totally be out of scope here in this short part. And
so
you need
So the condition number does not affect the number of iterations here in your.
The condition number does affect the number of iterations. So yeah, also it just can be seen in the long version of the talk is that you have short curved parts, and the length of the curved parts is dominated by the condition number, and you have long straight parts of which you only have strongly polynomially many. These straight parts are not depending on the condition number, but the short curved are. Yeah.
Okay, great. Thanks a lot, Bento. I guess at this point you can stop sharing your screen. Thanks a lot for the talk. And our next speaker is Jan van der Brand from KTH. He's going to talk about solving tall, dense linear programs in near linear time. Jan, can you hear us?
I can hear you. Can you hear me?
Yep, loud and clear. Stage is yours.
Right. Yeah, so I want to briefly explain how to solve tall, dense linear programs in nearly linear time. And this is joint work with Yin Tetley, Aaron Sidford, and Zhao Song. So we consider the following type of linear program. We want to minimize the inner product of some cost vector C and the solution vector X. And the solution vector X needs to satisfy these linear constraints. And this matrix A, we want that one of these dimensions, so let's say this dimension n, we want one of the dimensions to be much larger than the other dimension. And we also assume that this matrix is dense, so at least some constant fraction of the entries are supposed to be non-zero. And then you can show that there is a conditional lower bound for this type of linear program. It's unlikely to beat nd plus d to the omega time. Here omega is the matrix exponent, so the time you need to multiply two d by d matrices. And here in the last column, I assume that n is at least something like d squared, just to simplify the complexities a bit further. And if we assume that n is actually roughly the same as d, then there already existed an optimal algorithm. So if n is roughly the same as d, then this d to the omega and n to the omega term are the same. But if n is much larger than d, then this algorithm is far slower than these lower bounds that we have. So the question remains, for the more general case, when n is larger than d, how fast can we solve this? And if we look at the history of algorithms based on the central path method, then we see that all of them, they are slower by some polynomial factor compared to the lower bound that we have. And now our new result is that we get an upper bound that runs in nd plus d cubed time. And this is optimal if we assume that we don't use fast matrix multiplication. So if we say that here this omega term is just 3, then this would be the best possible upper bound that you can get, conditional on you can't solve linear systems faster than this. Alternatively, if we assume that n is sufficiently large, at least something like d squared, then our upper bound simplifies to just nd time, which means our algorithm is nearly linear time in the sense that the complexity is basically bounded by reading the input matrix of the linear program. All right. Now, how do we get such upper bound? How does our algorithm work? So the very rough high-level idea is that we have a new type of central path method and a whole bunch of reductions that show that if you want to solve some linear program, then instead you just need to solve two data structure problems. One is called inverse maintenance. That's a classic problem that has been studied a lot. That's about trying to maintain the inverse of some matrix M, where the matrix M is allowed to change over time. And now our new data structure problem that we try to analyze here is some kind of heavy hitter data structure. This is about you're given some matrix A, you're allowed to preprocess it, and then we want to very quickly answer queries where for any vector h that we are given, we want to find the large entries of A times h. So we don't want the entire matrix vector product, just the large entries. And if you have fast data structures for both of these problems, then our reductions and central path method show that you can get a fast solver for linear programs. So the summary here is we have this new central path method, which reduces solving linear programs to do two data structures. And we provide some data structures that then give this nd plus d cubed time linear program solver. But this framework is quite general. So it's likely that you can improve this upper bound further if you assume that you don't solve a general linear program, maybe some specific optimization problem that can be written as an LP. for the open questions, one thing is that the actual lower bound, the conditional lower bound, is that you need to read the input. So we have some z plus d to the omega time. Z is just the number of non-zero entries in your matrix. Now, if the matrix is dense, then this Z is ND, so exactly the same as our upper bound here. But it could be possible that you can improve this upper bound then from ND to just have this Z factor here. Alternatively, another open question is, can you improve this D cubed term in our complexity to be D to the omega? And yeah, if you have questions, then let's hear them.
Okay, thanks a lot, Jan. Any questions for the crowd? Okay, if there are no questions, maybe I'll... Yeah, sure.
Yeah. The first question was, in my picture, the matrix was actually fat, not tall. Yes, so I didn't have space to put in a tall matrix, so I wrote A transpose and made it fat. So we consider tall matrices where A is much taller. It's just that in that specific slide, it looked fat instead of tall because I transposed it.
Okay, the second question is, the picture gives A transpose.
Okay, someone answered the question already.
Yeah, I think that's about it. Are there any more questions? Jan, so maybe you can say a word about what prevents you to have the solution for sparse matrices?
Right, so so our data structure is based on what's it called? L2, L infinity heavy hitters, sparse retrieval framework. And what happens is that we basically compute some kind of matrix product. And even if our initial matrix is sparse, after multiplying it with this other matrix, it just becomes dense. And we don't know how to improve that.
Mm-hmm. Okay, great. I see Anupam has another question here. You mentioned improvements for specific problems. Can you give some example of an application?
Right, so there's a follow-up work where if the constraint matrix is an incidence matrix, then you can solve it faster. So these are some new data structures, specifically if the constraint matrix is an incidence matrix. If you plug this into this framework, you get some n squared time bipartite matching solver. I think it should be on archive within a few, at latest with the soda deadline, I think. But in general, I think that basically, if you have an optimization problem where the constraint matrix is very structured, if you can find some data structure for this heavy hitter problem for that specific constraint matrix, then that should already give a faster solver than what we have given you for general linear programs.
Okay, great. Last question. I guess it's the question about improving the n cubed to n to the omega. What's...
Okay, so one issue is that we have a whole lot of approximations inside the data structures and the IPM, the interior point method. And in order for the solution to actually stay feasible, we have to use a very accurate spectral approximation, something like, what was it, d to the 1/4? So basically what happens is we have root d iterations of the IPM, and in each iteration we need d to the 2.5 time because we just need an accurate enough spectral approximation. I think it should be improvable to d to the 2.5. I don't see how to improve it to d to the omega, because the classic algorithms that get something like n to the omega as an upper bound, they kind of pre-compute a lot of information that might be used in the future, but that automatically gives you some dependency on n, where you have like all the possible rows of your matrix.
Sounds good. Thanks a lot, Jan. I guess we can move on to our next speaker. So our next speaker is Swati Padmanabhan. She's going to speak about positive semi-definite programming, mixed, parallel, and width independent. So Swati, whenever you're ready. Swati, we cannot hear you. Maybe you're still muted.
Hi, sorry. Can you see my screen?
Yeah.
Okay.
Ready when you are.
Yeah. Okay. Okay. Sorry, hang on. Okay. Thanks for the introduction. This is joint work with Arun Jambulapati and Kevin Tian, both graduate students at Stanford, Jerry Lee from MSR Redmond, and my advisor, Intat Lee at the University of Washington. So I'll first start with defining positive semi-definite program. You're given PSD matrices P1 through PD and C1 through CD, and you want to find the minimum positive number mu such that there exists a d-dimensional vector X, which is element-wise non-negative and satisfies these two constraints over here. These inequalities are in the PSD sense, and you can view these two constraints geometrically. So if you think of the identity matrix as a sphere and recall that any PSD matrix can be associated with an ellipsoid, then the first constraint asks for the scaling factors xi's such that the scaled sum of these pi's can be packed into a mu scaled sphere. And similarly, the second constraint asks for the same scaled ci's to cover this unit sphere. So these are the packing and the covering SDP constraints. You might have seen packing and covering LPs before, and you might also know that they are dual to each other. But the difference from the LP setting in our setting is that packing and covering SDPs are not dual to each other. So as a consequence of these two facts, what we have is that if you solve a pure packing LP, then you can immediately get a solution to the pure covering LP by strong duality. But this doesn't hold in the case of SDPs. And a prominent example of a pure covering SDP is the max cut SDP, as was given by Gomez and Williamson. And before our work, there was no efficient width independent algorithm for solving these SDPs. And I'll define the word width soon. So there are quite a few prominent applications of this problem, such as graph spacification, robust statistics, and multi-commodity flow. Before I describe our contributions, I would just like to define the three adjectives in the title of our paper: mixed, parallel, and width independent. So the word mixed refers to problems which have both packing and covering constraints. And if you have only one of those, we call them pure packing or pure covering. The word parallel refers to an algorithm in which all the coordinates of X are updated simultaneously. And in the case of in this SDP setting, we define width as shown here. Note that in the case of packing and covering LPs, width is defined slightly differently, but it can be interpreted in the same analogous manner. So with these definitions in mind, here are our contributions. We give the first algorithm for solving mixed packing covering SDPs, that is parallel and width independent. And our iteration complexity is epsilon to the -3. When we specialize our algorithm to the case of pure packing SDPs, we improve upon the previous best result for this problem. So the previous best result for this problem was by two separate teams of researchers, Alan Zhu and Norekia, and Peng, Tanggong Sang, and Zhang, both in 2016. And the iteration complexity was epsilon to the -3, which is now epsilon to the -2. And when we specialize our algorithm to the case of pure covering SDPs, then as I mentioned, we give the first parallel with independent algorithm for this, efficient with independent algorithm for this. So I'll just give a one-slide summary of our techniques. At a very high level, we generalize a paper of Mahoney, Rao, Wong, and Zhang from 2016 on mixed packing covering linear programs. There are two main bottlenecks to overcome in doing this generalization. The first is that covering constraints are generally harder to work with than packing constraints. And all previous results in this packing covering LP had an asymmetry in the two cases. So one of the things we do is to remove this asymmetry in the algorithm between packing and covering. The second bottleneck is in going from the LP to the SDP setting. And that's because many vector inequalities simply do not generalize to the matrix setting. And a simple example is just like the exponential. So basically to achieve this generalization, we use tools from linear algebra, such as Schur complement, and we derive a matrix version of the Cauchy-Schwarz inequality and open up the proof of Lieb-Turing inequality instead of using it as a black box, and many other such ideas. And that's all I have to say, and I'll be happy to take any questions. Thank you for your attention.
Thank you very much, Swati. Any questions for Swati? I see one question by Tachafal. Are all the works you mentioned randomized? What is the fastest deterministic algorithm for solving packing or covering SDPs?
Yeah, ours is randomized. Like we use Johnson-Linden-Strauss lemma. I do not know what is the fastest deterministic algorithm.
I see. So you use this for sketching the and for using the
like in the gradient compute. So our algorithm is you compute the gradient of a packing potential and a covering potential, and those gradients are computed using Johnson-Linden-Strauss lemma.
I see. And that's being done in order to speed up the algorithm, right? That's...
Yeah.
Okay, thanks. Another question by Vasilios. Are there any results that obtain improved iteration complexity for these problems without requiring the updates to be parallel?
So in the SDP setting, in fact, we do not have anything at all for the mixed packing covering case. I mean, there are different cases. So if you specialize to LP setting, then if you just look at pure packing or pure covering LP setting, then yes, the fastest result, there is a work by Alan Zhu and Orekia, and also by Wong, Mahoney, and Rao, which actually get a much better runtime for that LP setting. And those two algorithms are sequential. So for different cases, there are different results you have.
Okay, thanks. And I guess another related question by Arvindan. Does this also imply better sequential guarantees for approximately solving packing or covering SDP?
Yeah, I haven't thought about the sequential thing at all, but I will think about it and I'll get back to you.
Yeah, I guess Arvindan is happy. He says that it might have been answered by your previous question. So great. So if there are no more questions, thanks a lot, Swati.
Thank you.
Sharing your screen, and we can move to the last talk of the session. Yang, can you hear us? Yang?
Oh, I'm here. Yeah, let me just share my screen.
Okay. So our last speaker for the session is going to be Yang Liu from Stanford. He's going to talk about faster energy maximization for faster maximum flow.
Hi, everyone. I'm Yang, and this is joint work with my advisor, Aaron Sidford, about faster algorithms for exact maximum flow. So just to recap, the maximum flow problem is you're given a graph G with a source vertex S and a sink vertex T, and I want to route a flow on the graph. A flow means that every vertex has the same amount of flow in and out, except for S and T, and I want to route the max amount of flow from S to T without violating the capacity constraints. There's been significant work on this problem, starting from the earliest algorithms of Karzanov and Evan Tarjan that got an m to the 1.5 runtime. More recently, there's been a lot of work on it in the lens of interior point methods. And there's been m root n and m to the 10^7 algorithms for, let's say, the unit graph case. The main result of this work is we give an improved algorithm in the case of unit sparse graphs, m to the 11/8 time algorithm for max flow. I guess I should convince you that 11/8 is less than 10^7, which is the previous best result. And you can see 10^7 is 3/2 minus 1/14, and 11/8 is 3/2 minus 1/8. So once again, this gives a bipartite matching algorithm and also just an ST cut algorithm, all in time 11, m to the 11/8. So to briefly describe what our strategy is, I'm going to still use an interior point method. The setup is from Madri 2016. And in interior point method, you set up this thing called barrier function. So intuitively, the log barrier function makes sure that you don't violate the capacity constraints with the logarithm terms. And the weight terms, the WE plus and WE minus, they tell you how much you care about each barrier term. So the interior point method generally keeps the weights as all ones, but a lot of the new innovations involve changing the weights to make more progress. So our main new approach is an efficient algorithm to compute good weight changes. The way that the weight changes were done in Madri 2016 was you kind of combinatorially double the resistances or increase the weights of edges that have large electric flow. Instead, in our work, we're just going to solve a one-shot optimization problem which we call an energy maximization problem to solve for the weights. And on the next slide, I'm going to describe what the energy maximization problem is. It's kind of what it sounds like. For every edge, you have a weight budget, a cost CE, and you have a total weight budget I'm willing to spend. So I can increase the resistances by 1 for cost CE, and I want to maximize the resulting energy of the electric flow. So kind of written as an optimization problem, it's max over the constraint of the energy. Now we know the electric energy is the min 2 norm of the flow, and then you can flip the max and the min and do a calculation to kind of get this final result. That it becomes a flow problem where you want to minimize overflows of the 2 norm plus some infinity norm term. So now we need to solve this. To solve this, we use some recent work of King, Peng, Sachdev, and Wang, which shows that you can't solve it with the infinity norm term because that's kind of equivalent to max flow, but you can solve it with a very high powered P norm term. So while there's significant in like reducing from what we need to the known result, it does eventually work because we have some slack to deal with, and that's how we get a result. Okay. So as for what are future directions, I think one thing is this King, Peng, Sachdev, Wang result only works in unit graphs, and I think extending that to weighted graphs could have implications. Other things I think are interesting is I think our method like starts saying maybe you don't necessarily need to use like electric flows or interior point methods to do maximum flow. So I think that's interesting. And also ours only works in unit graphs also. So what can we extend it beyond that? Finally, I want to mention that recently we've been able to actually improve the algorithm to get an m to the 4/3 time algorithm for bipartite matching and unit max flow. And also that it's been extended by AMV to min cost flows. Okay, well, that's my talk, and happy to take any questions.
Okay, thanks a lot, Yang. Let's see. I see Salil has a question. Where does the 11/8 or 4/3 term come from?
So So the way these things work generally is there's kind of a trade-off. On one hand, every iteration I take, I need to perform some weight changes to make my next step large, like larger than the 1 over root m, which naturally comes from an interior point method. Yeah, so there's just some trade-off you have to do there. I don't have a good intuition for why we're really stuck at 4/3, but yeah, that's at a high level where the trade-off comes from.
All right, great. Another question, if your graph is dense, can you get m times n to the 3/8?
So I guess the only things known to do that, at least in the max flow case, are using like things like the Lee-Sidford barrier, and I don't think that plays really well with the current weight change methods done in this paper. So I would say like it's either very difficult or requires like significant new ideas.
Okay, great. Maybe I'll ask one question. So do people generally believe that the final answer should be close to m in terms of, you know, close to linear in m?
Yeah, I think it should be linear in m, but I'm not, yeah, I think it should be linear in m, but I'm not so sure whether it's going to go through interior point methods or kind of be through some different method. It's unclear.
All right, any more questions for Yang? There's another one here. Can you hope for an improvement if the solver from the King et al. Paper can handle weights on the LP term? So
so the question was whether if you can improve the solver from the King et al. Paper to handle weighted p-norm flows, whether I can get any improvement. I don't know how to do that. I don't, yeah.
Mm-hmm. All right. It seems that this is the end of our session, pretty much. So there are quite a few people in the audience here. I think the common practice is to hang out for another like 15 minutes or so. So thanks for all the speakers and all the audience for showing up, for asking good questions, and enjoy the rest of the conference, be safe, and we can feel free to either hang out a little more, interact with the speakers, or continue the discussions on the Slack channel. So thanks everyone, and have a good rest of the day. Thanks, Jan.